All right. So I'm going to talk about district scale characteristics of the Cobar field. So my name's on there, but it's not just me. A lot of this work was done by Peter Downs, who's now retired from the Geological Survey. Phil Blevin had his hand in it, and we got a lot of help from other government agencies like GA for our geochronology and collaborative work that we do with JCU for ICPMS work. And of course, none of this would happen if the explorers and the like didn't let us in. So there's been a lot of core that we've looked at over the time to get to where we are. So, oh, that was good. So I'm going to talk about these sorts of features. So when I said district scale, it's obviously the favourite things that I've got. I'm going to talk about geochronology. So we'll have a quick look at the intra-basin magmatism of the Cobar Basin. We'll look at geochronology of faults and foliations in the basin, and then the geochronology of mineralisation itself. And we'll sort of meld from that into lead isotopes and the spatial variation of these isotopes across the basin. And all of that will sort of end up in this three-stage model that we've sort of come together with. And that's by no means a final model. The more data we collect, the more the model changes. So I've never said that we've got to the end of it. We constantly are surprised by what comes back from some of these ore bodies. So this one in particular, which is a recent favourite, sample supplied by Carol Simpson from Peel of cassiterite from Mallee Bull associated with the copper mineralisation that was dated. So I'll just give a quick overview of the Cobar Basin. Have I got my laser pointer? Look at that, the fiery pointer. The basin was extension and basin deposition pretty much occurred between 420 and 405 million years. It deepened rapidly, and volcanism was going off early in the sequence, in the deepening, and then gently interfingers in a couple of troughs, or not gently, but interfingers in a couple of troughs till slightly later in the basin history. And then the whole thing's blanketed by this light blue material, which is this amagmatic turbidite sequence of the upper amphitheatre group. Basin was inverted between 400 and 380 million years, and there's mineralisation throughout the basin, polymetallic, and it's always been an enigmatic genesis. A lot of people believe in VMS, a lot of people believe in orogenic base metals. Recently we've come up with some skarns, and really it's probably a mix of all of them, as you'll see as we go through. So I'll just go a quick look at the time-space plot for Cobar. So obviously time on this axis and space. So this is the eastern side, this is the western side. Magmatism, it ranges between, intra-basin magmatism ranges between about 423 and 409 million years, so up to this sort of Pradoli gap. And the sedimentation is about the same. So our fossil record says that the Allura limestone that sits underneath the Cobar sequences, the Nurry group or the CSA siltstone, is Lockovian, so somewhere just above 420 million years, and then we get Praguean limestones in these shelf sequences. So geochronology and fossils are saying similar things. But also the basin sits over the top of it's very hard to read this stuff. The basin sits over the top of a sort of a broken basin sequence, a basement sequence. In the east you have the Gerolambone group, and in the west the basin is sitting over Adaminaby group. Obviously the Gerolambone group has mafic volcanic associations, whereas the Adaminaby group and Bendot groups are more sort of straight turbidites with black shales as the extra part of their system. So let's keep going. So if we look at the magmatic geochronology, it ranges between 423 and 409, like I said. It's a shame my squares have come up completely wrong. I don't know how that's happened, but that's all right. Well, this is going to be fun. So the majority are between about 420 and 417 million years. In the west of the basin, we have an S and I type association mostly. In the east, an I and A type association. But with that volcanism, we see that all volcanism, even the stuff in the lower parts of the sequence versus the volcanism higher in the sequence, basically everything comes back at 420 million years. So we've got a really compressed stratigraphy that we're actually finding hard to resolve geochronologically. If I go for a couple of highlights, I'll just show you some issues. So it sounds simple. We've got a 420 MA basin with magmatism at 420. But some areas, like this area in Normavale off to the west, just on the northern part of the Mount Hope Trough, this is the Mount Hope Trough, one of the volcanogenic troughs. Here we get diorites, which is this red thing, and S-type granites together. They dated around between 427 and 423 MA, so they're dating it older than the basin sequences. Yet it would appear that they are sitting within a sequence that has been mapped in the middle of the basin sequences. So we've got geochronology problems still, even in the magmatic systems. If I move across the basin to Mallee Bull, there's these rhyolite bodies or domes as they're being considered now. They're at close to 420 MA, and they sit in stratigraphy, which is this Schum formation, which sits close to the top of, or right in the middle of our basin sequences, that traditionally we've thought was younger. We thought it was closer to 410 million years. So again, we're seeing this really compressed stratigraphy that we can't seem to resolve any time relationships in. Rabbit Hill was something that we got some samples from a little while ago, and this is sort of the expression of the youngest magmatism in the basin. So this is off to the east, east of the Cobar field, up here in the Maramba group, and we're getting little dacitic sills, I-type hornblende dacitic sills at about 410 million years. So that's about the end of magmatism in Cobar. All right, so I'll quickly skip to deformation chronology, geochronology. So deformation, what we see is that our faults and foliations, and I'm talking about unmineralised systems here, is they generally span, my phone's gone to sleep. They generally span, we see just a spatter of ages from about 405 million years all the way to about 370 million years. Now this includes survey data and old data that has been collected over the years through Argon. If you start to try and do a traverse or have a look at where these things are forming, the older systems that we've come across, one was again in Normavale, in the diorite itself there. We get these faults that have got hydrothermal alteration with them and a lot of hydrothermal titanite developed. So we definitely know that we're seeing movement on faults, potentially an extension of the larger Boothra-Gandra system up to the north at about 404 MA. So that's about the first signs we see of unmineralised deformation. In terms of foliation, we've done a lot of data, and this doesn't actually have them all on there, but we see ages coming back at around 395 to 390 million years for basin, the start of widespread foliation development during basin inversion. Then we get late structures, so deformation's still going on, but we have late vein systems and thrusts. A lot of these are well expressed chopping up loads on ore bodies, so you see them at Hera, you see them at CSA. Again, we can date these, and they're coming out slightly younger, 380 million years. So we've gone from this ductile system to this more brittle thrusting or brittle faulting system. Then we can look even further. Sometimes you see discrete shear zones through some of the granites. And we've done some argon work on one in particular off the Nymagee-Igneous complex. And these are coming back quite young. So there's movement on the major fault systems on the eastern side of this basin down to about 370 million years. So as a quick summary of that, we see one lot of faults, the oldest ones that we get that are unmineralised at about 405 to 400. We definitely see foliation development somewhere between 395 and 385. And then we see later brittle systems developing later in the system down to about 370 odd. And that's it. So, if I now move on to alteration in gang geochronology. So we've done our magmatism, mostly 420. We've got our three-part system for deformation, 405 to 400, all the way down into those sort of foliation development at 390, 395, and then some late 380 to 370 movement. So this plot here has age in millions of years, and what I've done is I've distributed all of the dates for mineralisation. I've plotted according to their zones in the basin. So Mineral Hill, Cumbelligo, Hera, Cobar Field, Central Basin, Mount Hope Trough, and the Windduck Shelf. We don't have any dates for the Windduck Shelf. Well, I don't. So what you can see is that from these, you can see, for example, Mineral Hill, Cargeligo Belt, we're getting older ages in that lower volcanic packages. We're seeing 420s to 410s. Actually, I'm not actually up to that. I think that's how I've got well ahead of myself there. So the easiest way to think about this is three systems. So we've got the old ages that we're seeing in mineralisation that are associated potentially with volcanism. So we said our magmatism was around 420 MA, and we are seeing an expression of those ages. But then we've got this big zone, which includes a lot of the main mineralisation in Cobar that sits somewhere between 410 million years and 400 odd million years. And then we definitely have a later set of ages that are coming out mineralised, usually lead, zinc, silver, that are somewhere between 395 and probably 375 million years, consistent with what we saw in the geochronology of our fault and foliation systems. So if I do a quick traverse across the basin, this is where I was going. Mineral Hill, Cumbelligo. So Peter Downs did some dates up this belt. And yeah, they come out quite old. They're at the 400 to 410 range, consistent with what has been thought to be there, which is epithermal systems for Mineral Hill, and Pipeline Ridge, for example, which is a deposit slightly further north. Up in here, it's thought to be a VMS style system, I think now epithermal type system. So it's an area that's related to the volcanism that's going on, and it's showing older ages. If we move further to the Cobar mineral field, we get a completely different set of ages. So the main copper gold systems, this is like including Peak, CSA, Kronos, all of those systems are coming out consistently at around 410 million years. We can find the minerals to date inside the ore, like the titanite inside CSA, titanite here at Perseverance, inside the mineralised systems. But then there's a second set within the Cobar mineral field, and these are the ages for deposits like Allura, the lead, zinc, silver systems. These are for the lead overprint on Peak. So we're seeing there's definitely two systems operating here. One at about 410, and then our classic inversion phase ore bodies, which are the lead, zinc, silver systems, developing somewhere between 380 and 390 and 380. If we step to the Hera Nymagee zone, slightly different again, but similar. Somewhere between 410 and 400 million years, we're seeing most of our mineralisation developing. Again, we get beautiful hydrothermal titanite preserved, intergrown with our ore minerals and our main alteration minerals. But of course, there is one younger age, a mineralised age, which was gotten by Peter Downs. It's an argon-argon age. So there is evidence of this sort of piggybacking that was on Hera, of this sort of piggybacking of later lead-rich systems or lead-zinc-rich systems on what was already there. So particularly for the Hera zone and the main Cobar field, people have suggested a sort of magmatic flavour, and I think I've given talks before on the skarn-based assemblages that we see through Hera and Nymagee, and I think we're getting some pretty compelling evidence that there probably was some sort of magmatic input to this system at 410 to 405 MA. If I move into the central zone, these are some new stuff that we just started doing with Peel. They found cassiterite, plenty of cassiterite associated with their chalcopyrite mineralisation at Mallee-Bull. We could date that, and it comes out beautifully at about 420 million years. So that's syngenetic essentially with the volcanism that's going on at Mallee-Bull. In saying that, we do also get later ages, so we dated some biotite salvages for example, around some of the main sulfide, or some sulfide veins, and they have definitely formed during the inversion phase. Yeah, so there was the key there is there was mineralisation at Mallee Bull, even if it's just tin, at the same time as volcanism. It's probably the first time we've actually been able to pinpoint something directly. And then if I move west again, this is where it gets a bit messy. So Southern Nights, Wagga Tank, and Blue Mountain. Southern Nights had a spread of argon-argon ages for adularia and cerussite, somewhere between 410 down to 400 MA. These were dual plateau plots or plateau plots. They were quite messy, so it's, I wouldn't hang my hat on these ages yet. We're still doing some more work. But one there that was interesting was the adularia at Blue Mountain, which is here. So adularia at Blue Mountain, as a part of that system, replaces fossils, and all of the sulfides are in there with adularia replacing the fossils, and we got a good 370 million year age for that adularia, suggesting that the replacement at Blue Mountain is probably an inversion-related phase of the system. So, quick summary. 3 main phases, the 420, the 410 to 400, and then the inversion-related systems at 390 to 380. But also we're seeing different zones express different ages of mineralisation, and often multiple. So I'm going to do lead isotopes. This is all basically mostly Peter Downes' work. Sorry to get into isotopes, it's not my favourite field, but obviously lead is, the lead isotopes that we use are a common lead 204, and then we use the radiogenic isotopes against that common lead essentially, which are developed through the breakdown of uranium and thorium. So I need to read this myself a little bit. So yeah, basically look at the ratio. So if you think about a lead reservoir, the lead is a mix of minerals basically sitting in that basin sequence. Let's go with our initial sequence here at 420. Uranium and thorium evolved to the point where you extract that lead from the system. And if you bind that in a high lead mineral, there's not enough uranium and thorium to change the lead ratios that it already established. So once you rip it out and develop an ore body, it'll save the lead isotopic ratio of that time. And we can do that several times. So you can then go for another, say, fault movement during the SAG phase at 410 million years on this basin, and our systems continue to evolve inside the basin reservoir, and then we extract again that lead, and we preserve a different isotopic ratio, a slightly more evolved one. And then we can go to inversion, and exactly the same. It's been sitting there evolving, and we'll extract lead. Our galena will have a different isotopic ratio that's slightly more evolved again. So the normal things that we go for are, out of these systems, using lead is a lead source and a lead model age is the two main things that we're after. So lead source doesn't matter so much in Cobar, it's crustal, so these are the lead growth curves that have been made for the system there. This is just the I can't read which ones they are, 207, 204 and 206, 204. And so, but what we do see in Cobar is we see, of course, variation through time in the lead isotopes. So all the way from about 440 to 370 MA. And then if you plot those spatially across Cobar again, you see that different zones have different lead isotopic signatures. So, for example, Mineral Hill, Cambeligo and Mallee Bull have quite old lead, whereas somewhere like Endeavour and the Mount Hope Trough systems, Southern Nights and the like, they have quite young lead model ages. So I thought it would be easier for everyone if I plot this as a box and whisker style plot of just lead model age. So on here is the lead the age in millions of years, and these are the different zones across the basin. So if we have a quick traverse through, we see we've got these more older lead signatures in the Mineral Hill Cambeligo belt, some of them getting a little bit too old for the basin, and there's probably other reasons why they are. And then we skip over into the Cobar field, and we've got a beautiful set of sort of 400 to 410 million year lead, particularly from the copper gold systems. And then we've got younger lead in things like the CSA lead lodes and Endeavour, that's more inversion related around that 380 million year age. Skip over to the Hieronymus field. Again, we've got a nice set of lead model ages sitting somewhere between 410 and 400 MA. So our mineralisation's really coinciding well with the uranium lead systems, with the other dating systems. If you have a look at Mallee Bull, it's always been a shag on a rock. It's always looked too old. Everything else in that area fits in this sort of 410 to 400, but Mallee Bull always looked too old. We'll get into that. And then if we go out into the Mount Hope Trough, you can see everything from 400 to sort of 380, 370 full inversion phase type lead model ages. So if you compare that directly with our geochronology, we have our phase 1 that I was talking about, something that generally coincides with volcanism, sort of fits quite well with the volcanic Mineral Hill Cambeligo volcanic belt. We see some of these old lead essentially in there, and we get all the way up to that sort of 410 lead, which we do see. Then Mallee Bull, we have our new cassiterite date there for 420 million years, and all of a sudden the lead isotopes don't look so far out of whack. It's potentially got some old mineralisation there. Then we have our second phase, which is this 410 to 420. That's our central, our Cobar mineral field. So if we have a look at Cobar mineral field, very, very similar with the younger dating, isotopic dating, and younger lead model ages for those lead zinc ore bodies. Here in Nymagee zone, almost identical. A bit of older lead at Nymagee, which can be explained in other ways. Again, Mallee Bull looks very similar, but we have a bit of a mismatch with any of the younger parts of the system that we don't seem to see. And then the one that really stands out is, and then we have our last phase, of inversion phase stuff, which is our Endeavours, our lead zinc systems. And in there is this Mount Hope trough system. I'll just check I know Yame's going to tell me, but I'd like to know. Mount Hope trough system. So the mismatch here, we have a huge mismatch with the geochronology so far. Geochronology suggests, our alteration dating suggests that it's older, but our lead model ages are younger. Potentially we're looking at this sort of scenario, where Luke's got Yoda on his back. Well, maybe we've dated Yoda and not Luke. And the next thing we can look at through this system is sulfur. Sulfur is also zoned through the Cobar system. So the simplest way to look at sulfur is geologically important reservoirs. So people have characterised what magmatic sulfur should look like, and people have characterised what reduced seawater sulfate should look like, particularly for Cobar. Downs and Seckham, I think, did the Cobar one, and Downs and Poulsen, I think, did the Central Lachlan igneous rocks. But what you essentially see is that everything from Mineral Hill Cambeligo, Hera, everything on the eastern side of this system is somewhere either a mix between what would be an igneous system down here at the lower Del 34S to just into these basinal systems. And then in the Hieronymus zone, where we see our skarn assemblies, our most igneous looking material, we get straight igneous sulfur signatures. So, and then as we head out to the Western Basin, it's all dominated by reduced seawater sulfate. We're not seeing that igneous input into our sulfur source. So there's a fundamental divide going on in sulfur. I just put this in because there is other evidence for magmatic input, particularly in the Hieronymus zone. The sulfurs suggest we had a magmatic sulfur input. We've got garnet-rich skarns, distal skarn assemblages developed at Hieronymus. They have all the signs of being a distal magmatic system. Even the oxygen-hydrogen isotopes that we did on them down here, they suggest that we've probably started in a field consistent with magmatic waters, and slowly they've mixed with formational waters through time. 25. So all of this goes towards making greater models for the basin. So This is just the start. This is this rift phase, this 420 to 415 MA phase, where volcanism's going off in our troughs, volcanism's going off in the Mineral Hill Cambeligo belt. We've got some basin highs, and the basin's starting to deepen rapidly. I've recently added Mallee Bull to this because of the age dating from the cassiterite. But so that's the sort of first phase of the system that we see. Then obviously the basin deepens a lot, and by about 410 to 400 is the best guess. You've seen most of the sedimentation already happened, and we see fault movements, we see deformation even without mineralisation, but then a lot of our mineralised zones are turning up at about this age. So we're seeing a major movement of faults between 410 to 400 MA to produce these epigenetic Cobar type bodies. But as we said, a lot of those look like they've got some sort of magmatic input to them, and we know we've got magmatism down to 410 from Rabbit Hill. So the suggestion would be that we've got this sort of magmatic input that we're just not getting to see at the exposure levels at Cobar. That's also helping drive these systems between 410 and 400 MA. And then of course we've got the final systems. So we've inverted the basin between 390 and 380, and we're seeing mostly basin-derived fluids that are being pushed up faults. Mineralisation's piggybacking off other mineralisation to produce lead, zinc, silver-rich systems. We're getting new big ore bodies like Endeavour or Allura. And again, consistent with all of our dating. Yeah, so summary-wise, it's just follow the data with Cobar. So the more we can get, the better. I mean, we haven't gotten to the bottom of every one of these systems yet. I know that I haven't gotten the oldest age I can out of the skarns at Hera, for example. But we're doing our best, and we're coming up with a more and more consistent picture, and different methods are agreeing, which is what's really nice. So we see the I of the A magmatism at about 420 million years. We see faulting evidence at about 405, foliation development 390, and then renewed faulting and the like, or continued all the way to 380, 370. But mineralisation we're seeing in three pulses. We see the 420, which is likely related to the volcanism. We see the 410 to 400, and that's epigenetic. All of that stuff, they are not parallel to to bedding or anything like that. They're structurally controlled systems. They have a magmatic flavour, and we know that faults are active at this time even without mineralisation in them, and we know that our magmatism just makes it down to 410 million years. And then we have a phase of epigenetic mineralisation, which is amagmatic, which is this lead-zinc dominated system that occurs during the basin inversion. And I just thought I'd mention that mismatch again between the lead and the argon at Mallee Bull. I mean, we're trying to get to the bottom of it. I think it was Sebastian at there that sort of got me on the right track. We're taking more lead isotope samples from their laminated ore systems to see if there's any changes, if we have just sampled a latent piggybacking system. But also want to do some shrimp dating of their volcanics just to make sure that our argons are not picking up magmatic ages in that system or the like. And that's it for me.